Good afternoon, everyone. My name is Begüm Genç. I'm a postdoctoral researcher working at Insight Center for Data Analytics at University College Cork. Today, I will be talking to you about one of our recent survey papers on explanation in constraint satisfaction that has been published in Int'l 2021. And before starting the presentation, I would like to thank to my co-authors, Sharmila Gupta and Professor Barry O'Sullivan from UCC, and also Ulrich Juncker for providing us lots and lots of feedback and comments on the paper. And also, of course, I'd like to thank Jean Freuder for inviting us to the 5th workshop on progress towards the Holy Grail. So today's presentation will be outlined as follows. We will first talk about the explanations in CP, like a motivational kind of beginning, and then I will talk about some of the terminology, the conflicts, the explanations or relaxations by going on some examples, a configuration example. And then I will also talk about the different directions that we have identified in constraint explanation in our paper, and also some of the next things that we are hoping the field is going to go towards. And by the way, you can find the slides available at the address given on the slide. So to begin with, why do we need the explanations? You know that the explainable AI has become a new hype. So mostly the machine learning or deep learning or neural network researchers are focusing on this term, saying that we need explainable AI, or XAI as the abbreviation says. And this is now creating a very big component of trustworthy AI, the explainability. So these learning applications, they are mostly behaving like black box systems. So people are just realizing that we really need to be able to explain them. But on the other hand, in constrained world, people have been working on these definitions for decades already. So people working on model-based diagnosis, constraint programming, or Boolean satisfiability, all those related fields, they were working on how to explain the systems. So now when we look at the trustworthy AI components, we want things to be ethical now. Ethical development is really important. And we want to be able to understand the solutions that we are producing. So we want to understand why am I presented a specific solution? So we're talking about some notions like transparency or explainability. And by assessing our systems, but we have come to the realization that actually sometimes our algorithms, but sometimes our data is biased, and we want to unbias these systems, and we want to provide fair systems that can be accessible if needed. So explainability plays a key role in the development of the AI systems. Now, when we look at the CP context, I will now talk to you about a few examples in CP that we may need the explanations. So one of the cases is the travel example. So let's assume that Aya wants to travel to Ireland from Turkey, and she goes online and she uses a flight finder, an engine that's using constraint programming in the backend. And she's giving all her constraints, and now she's searching for the flights, and there are no feasible flights with the constraints that she has provided to the system. And she wants to be able to understand why. And she wants to understand how can she find the next flight that is most similar to what she has been giving, for instance. Or another example can be given about the puzzles. So logic puzzles, think about the zebra puzzles, for instance. Assume that Bob loves solving those puzzles and he gets stuck in some of the states. And he asks the game for a hint so that he can solve the rest of the puzzle himself. But the hint that he receives from the computer, in his opinion, it makes absolutely no sense, because then he's stuck again in the game. Well, maybe he is just bad at solving it, or maybe the explanation, the hint that he received, is not really a helpful one, and he already paid for the hint, let's say. So he is just saying that I wish there was an alternative explanation, an alternative hint. Or similarly, let's say that Emma is a constraint solver developer, and she wants to do something clever, and she doesn't want to revisit the previous states in the search space that has previously violated a constraint. So she wants to omit those. So she wants to apply some sort of learning. So no good learning. And these were just the 3 examples that we may see in our real lives, but where else do we apply these things? Well, these things are widely applied in product configuration or test generation, and a hot topic nowadays is recommender systems. So we use these things in case-based reasoning systems, so like these constraint systems, or knowledge-based systems. In debugging, we also see this, and in software product lines. So in these areas, we can use constraints, and we may need explanation for those constraint systems. Now, I will start talking about the explanation and some of the terminology. So probably lots of you are already familiar with this configuration problem. This is a very famous one. So in this problem, we have 5 soft constraints or user constraints and 1 hard constraint, which is a background constraint. This constraint has to be satisfied at all times. There's no way that we can change this. So a user goes and uses this application to find herself a car. And these are her constraints. She says that my total budget is 3,000. I cannot exceed this. And I want a roof rack, I want a convertible car, I want a CD player in my car, and I want the car to have leather seats. But of course, each one of those properties has an associated cost. So, when we look at the problem, when we try to solve the problem as a whole, what we see is that this problem is infeasible. There is no solution for this. Why? Because if we try to satisfy all the 4 user constraints at the same time, we get a conflict with the 5th user constraint, which says that the total cost of all this is 4,100, which is exceeding your budget. And also, by the way, you want a roof rack and a convertible car at the same time, which is just not possible. And when we look at the constraints, we can, for instance, identify a conflict. And a conflict here means that it's an inconsistent subset of the user constraint set, U. So this one shows us one cause of the inconsistency. When we look at roof rack, convertible, and CD player constraints on their own, well, of course, we have the hard constraints still. What we see is that this is a conflict. It's just these 3 constraints cannot be satisfied together because they are violating the hard constraint that we have. And now think about the problem again. Use all the 5 soft constraints, and of course we have the hard constraint there as well. And I want to get rid of this conflict because this is causing me some problems. So what I do is that I start removing the constraints that are involved in my conflict. I start with removing C4. I say, okay, I don't want the CD player anymore. I will get rid of that. I want the roof rack, convertible car. My budget is still the same, and I want the leather seats. So I am finally able to reduce the total cost by removing one of the constraints in my conflict, but I'm still conflicting with this 2 constraints. So I go ahead, I remove another constraint from my conflict, and now I'm able to satisfy the hard constraint, which says convertible cars cannot have roof racks. I got rid of the convertible car, and unfortunately I'm still above the budget. And I remove the other constraint as well, so I completely remove my conflict from my problem, and then I'm finally able to get a solution. I'm finally able to find a feasible solution that's a partial solution in some sense. This solution only supports C1 and C5. So in another sense, we can also say that this C1 and C5 is a relaxation of the problem. So a relaxation is defined as a consistent subset of the user constraints. And this shows one possible way of recovering from the infeasibility. And then we can explain this. We can say that for instance, C2, C3, C4 was our conflict, we can either say that if we want the roof rack, convertible, and the CD player, the three of them together, there are no cars. So this is one possible explanation. But we can give a more detailed explanation, and we can say that by using the relaxation, we can say that there's at least one car within your budget that has leather seats, but this car doesn't have a roof rack, or it's not convertible, or it doesn't have a CD player. So these are alternative explanations that we can provide to the user. However, one thing that we need to keep in mind is that identifying one conflict and removing it only is not always a solution. So let's take a look at another conflict, C2 and C3. When you look at the two of them together, roof rack and convertible car, this is violating our background constraint. So this is a conflict. We cannot have this. And what do we want to do? We want to get rid of the conflicting scenario. And then assume that I'm removing the conflict as a whole. I got rid of the roof rack, I got rid of the convertible, and I'm thinking that, okay, I should be able to get a solution now. But I still want the CD player and the leather seats, which is still above my budget. So, well, unfortunately, there's another conflict in the problem. So removing one conflict is not always recovering the feasibility for us. And what are you going to present to the user by using this, for instance, as an explanation? There are no cars within your budget that satisfies both roof rack and a convertible property. However, if you get rid of them, there's still no cars satisfying the rest of your constraints. Well, this is not a useful explanation, so we need to do something more. And here we are talking about minimal conflicts. A minimal conflict is a conflict such that none of its proper subsets is a conflict. So when we look at this 4 sets here, each one of them is a minimal conflict. And these are all the minimal conflicts of this problem instance. So for instance, C2, C3, as we have seen before, is a minimal conflict. If I add C4 to it, C2, C3, C4, it's a conflict, but it's not a minimal conflict. And minimal conflict is being used within the constraint satisfaction area. But when we look at the neighbor fields, like the Boolean satisfiability, for instance, they are using some other terminology for the conflict, such as minimal unsatisfiable subset, MUS, or a minimal unsatisfiable core when we are talking about the formulas. Then, when we explain with a minimal conflict, it's again the same thing. So, for instance, when we only use the C2, C3, we can say that there are no convertible cars with a roof rack in the problem. Or similarly, we can provide explanations for C1, C4, C5. And in order to find a solution again, what do we need to do? We need to remove the minimal conflicts in a way that we recover solutions. So what can I do? If I get rid of each one of my conflicts, it means that I have no more conflicts because they were already minimal conflicts. If I get rid of them, there are not going to be any more conflicts in my problem. So when you look at the set of all conflicts, if I remove some of the constraints from each one of them, in this case, say C3, C4, and C5, I end up with C1 and C2 as my user constraints. And yes, this is a feasible solution. Now I have recovered the feasibility. And I can tell the user that there's at least one car with roof rack that costs less than 3,000 or equal to 3,000. But we don't need to remove too much from our problem. So in the previous example, there was C4 that I also removed. But actually now, when we look at a different terminology, so if we identify the hitting set of all the minimal conflicts of the problem, we end up with identifying the minimal exclusion set, which in this case a hitting set of this is C3 and C5, for instance, which is a minimal exclusion set. And if we remove those constraints from our problem, we end up with a feasible solution. Or in other words, if we relax these constraints, if we relax the minimal exclusion set from the problem, then we can find a solution to the problem. In this case, if we have the minimal exclusion set C3, C5, there's a complementary set C1, C2, C4, which we call as the maximal relaxation of the problem. So C3, C5 needs to be removed from the problem to find a feasible set which leaves us with C1, C2, C4. But there's not only one unique minimal exclusion set. Well, sometimes maybe there is, but I don't think. No, not in the general sense. We can have an alternative minimal exclusion set, which is C1 and C2, for instance, which hits every single one of our sets. And its complementary set, which is the maximal relaxation, would be then C3, C4, C5, which denotes a solution in our example. And the analogous term for this in Boolean satisfiability is the identification of minimal correction subset. So minimal correction subset and minimal exclusion set, they are actually referring to the same notion. And by using the minimal exclusion set, we can easily say that if you remove your minimal exclusion set, the identified minimal exclusion set from the problem, there is at least one solution. We can guarantee that. So now let's go back to the paper and what we have presented in the paper. In the paper, we have taken a look at all the research that has been produced for the last few decades, and we have decided that we are only going to look at the ones that are user-focused. Because when we are talking about trustworthy AI, we are talking about the user's point of view as well. And it's often the case that the user wants to understand why she was presented with a solution, or in some of the cases, she needs to interact with the system to understand which steps she needs to take to find the solution later on. In our paper, we have looked at the papers and we tried to categorize them under 4 different characters. So we are looking at the paper and trying to identify if the paper is doing some solver-specific work. So is there any coding that's specific for the solver? Or is the work solver-agnostic? So can it be applied to any solver? Then we are asking the question, for whom is this work being carried out? So is the explanation being created for the user? Is it a user-focused paper? Or are we trying to improve the search? So how to prune the search space faster, for instance? How do we end up with a solution or report that no solution exists? Then there's the measure of quality. So as I have mentioned before, the quality of the explanation is really important because this will affect the understanding of the user if we are presenting it to the user. Then in constraint programming, we have a couple of different notions. In some papers, people are trying to provide small enough explanations. So the assumption is that if you provide a long explanation, the user is probably going to find it difficult to understand the explanation. So it's not really going to do the work. So small is good. But maybe it should be a minimal explanation. There's no need to explain some extra other stuff when you are presenting it to the user. And then there's the minimum explanation, which corresponds to minimum length explanation. And then there's the quantity. So sometimes we want to present just one explanation to the user to recover feasibility, a single explanation. But in some cases, we want to provide a diverse set of explanations. So some representative, many solutions explanations. And also sometimes we just want to find or enumerate through all the explanations that are possible. So this affects the quantity. Now in the next couple of slides, I will show you in those bubbles the papers that we have reviewed and somehow the connections between them, but obviously it's way more complicated than this. And I have added a couple of words under each one of the paper, but the papers are obviously they contain way more information than that. But when we look at it, for instance, around 1993, the solver-agnostic approaches have started to become a very important thing. So Becker and the co-authors, they have identified, they worked on minimal conflicts, a minimal conflict. And then there's finding a minimal conflict idea has emerged, and people have worked on minimal conflict sets, or the famous quick explain algorithm by Juncker, which also has received the AAAI award a couple of years ago. And then there was Linz and Marques Silva that have proposed the minimum unsatisfiable core, and these concepts have been applied on model-based diagnosis, for instance, and it has been extended. And as some people, they have introduced the preferences, and they improved those models by using fewer consistency checks. And for instance, the corrective explanation work from O'Callaghan and O'Sullivan at some stage, how do we recover the feasibility, and also the quantified version of the constraint satisfaction problems. So the ones on the ones shown in orange, they are more recent research in the field. And then the model-based diagnosis applications, they started with using some hitting set trees or CS trees and some other trees that they have used for identification of the minimal conflicts. And then there's some more recent work, for instance, that has parallelized the previous approaches. And then Marques Silva and the co-authors, they have proposed the use of, they were using MaxSat algorithm for identifying minimal correction subsets, or in another word, which is similar to minimal exclusion sets. And people then identified a single or all minimal cardinality diagnosis by using SAT-based approaches. And then more recently, there's work on efficient enumeration of those minimal correction subsets. Then there's the quantity-related work. So some people, they worked on identifying all minimal unsatisfiable sets or all minimal conflicts. And the reasoning here was that the user not necessarily understands the explanation that we are providing them when we are providing a single explanation. So sometimes we need to find the simplest explanation in other ways. And there's some hitting set-based approaches that has been proposed by Bailey and Stuckey, which has inspired the work by O'Sullivan and the co-authors on the representative explanations. And then again, there's some work on the compilation. So Emil Hastre et al., they have compiled all the solutions, all the conflicts into an automaton, and then later on, this has been extended by using the user taking into account the user preferences. And there's also more recent work on identification of several minimal conflicts. Then there's lots and lots of work on Boolean satisfiability. And there are some systems that have been proposed for the identification of minimal unsatisfiable subformulas. And this is a very active field, and there are some exact methods as well as some inexact methods like locus search formulations, and they're not complete formulations or complete search, sorry. And then more recently again, there is the online minimal unsatisfiable subformula enumeration, and also the efficient way of enumerating these subformulas is a hot topic that's interesting at the moment. And very old work, some very ancient work in this area. Could be, we can say that it all started with maybe truth maintenance systems and assumption-based truth maintenance systems, which are consisting of a couple of components. And for instance, by the quick explain algorithm, Ulrich Jonker is solving one of the problems in this truth maintenance systems, the identification of a single conflict. And then by using these systems, we can end up with finding all the conflicts. And then there's lots and lots of work on how to improve the search, obviously. So some of the very famous and the oldest ones can be the dependency-directed backtracking algorithm and then the dynamic backtracking algorithm. And there's Freuder's work and Sabina and Freuder's work on maintaining a consistency algorithm, which is a very famous and still adapted algorithm, and also conflicted-directed backjumping as an improvement. And more recently, maybe, we have seen that close learning and no-good generation is really important for the learning phase and for explanation to the user. And there are some explanation-based solvers now. And we can also count the fact that there's debugging systems. So one can see the debugging systems as providing explanations for improving the search, but also alternatively you can say that debugging is providing the user some useful information for debugging their system. And then there's some work on explaining the global constraints and cumulative constraint and all different constraints. They have been attempted to be explained by those authors. And one of the main problems in explaining these global constraints is that there may be more than one decomposition of the global constraint. So your explanation actually depends on the way you're decomposing the constraint. And finally, there is the explanation of the puzzles. So we are mostly talking about how to provide, let's say, hints or how to tell the user how to solve the puzzle, so that maybe the ultimate goal could be to teach the user something. So the user can learn from the explanation and get better at the puzzles. And what else? This is obviously not the whole thing. So I really suggest for the interested readers to read Eugene Freuder's paper on explaining ourselves, human-aware constraint reasoning at AAAI 2017. This is actually really inspiring for understanding why we need the explanation and for whom are we trying to explain and why. So I really suggest that. And as I said, there's some work on debugging, so we can provide debugging for the user's understanding, and it's really important to be able to visualize these systems, because some people have just better understanding by visualization of the problems. There's some work towards there. And then, as I said, the Boolean satisfiability, the field on inconsistent formulas is very rich. And a recent survey from Marques Silva and Mencia titled Reasoning About Inconsistent Formulas would be a really good read for the interested readers. And for the future directions, our findings say that the current constraint programming systems, they usually focus on the performance. So when we're developing a system, we usually say that, how can I make the system faster? How can I report the feasibility or the infeasibility in the shortest possible time? So this is what we have in mind in general. But going forward, we can say that, how can I make this system, how can I formulate the system in an alternative way so that I can provide better explanations? Or how can I make the system more understandable? Or how can I write a system such that it uses the less amount of resources for trustworthy AI context? So these are some future directions. And there's another direction on the certifying solutions. So you provide the solution and then you certify it. This is a verification method. And there's also proof logging going forward, that if we log our proofs, if we use the proof logging, then we may be able to explain our systems and our judgment, or the system's judgment, in a better way. And I haven't included a reference slide in this one, but for the references that you would like to take a look, please refer to the reference section of our published paper. And thank you very much for listening to this session. I hope I was able to give you some useful information. And if you have any questions, I'm happy to answer them now, or you can simply send an email to my address there. Thank you.